Our first speaker is Tim Toohill. He is 6'7", and has actually never played basketball in any organized fashion. But miniature golf, done some miniature golf, Tim. Come on out.
All right. Thank you, Jake. Introduction. The way that was supposed to go was, if it stands that I play basketball because I'm tall, then it stands to reason that maybe someone plays miniature golf because they're not. But it was supposed to be a joke. So I'm Tim Toohill. I'm the CTO of Certus Group, and I'm here to talk today about some work that I did to integrate a large language model, a knowledge graph platform that I built. So this is primarily focused on development and data. I hear my mic going in and out, so that might distract me a little bit. But so yeah, this is primarily focused on, this is D4, but I'm focusing on the development and data parts. So what's next? So I want to talk a little bit about my motivation for trying to integrate an LLM with our knowledge graph platform. I also want to talk about why you would use a knowledge graph, and then the process that I use to integrate the large language model with the knowledge graph platform. And finally, I'll bring up the software platform that I developed and show to answer questions. And then finally, if there's time, I'm going to go over some ideas I've had for how to improve this. Okay, so I want to set the stage. Large language models are probabilistic. If you've ever used ChatGPT, it's been very much popularized. You'll know that for a given prompt that you give it, a question that you ask, it'll produce different output every time you ask the same thing. Not every time, but it can produce different output. And this is because LLMs are essentially a distribution of probabilities across tokens. And for the sake of this talk, you can think of as a token as a word. Tokens are not words, which is one of the reasons a large language model can make up words or hallucinate. But the output's probabilistic and not predictable. So what it's doing is it's performing a completion, and large language models have been trained on high volumes of natural language text, or the ones that we hear about are changed. So like the entire corpus of Wikipedia, source of training for these models. So, and based on that training, it builds the probability of what words would follow given a prompt. Databases, on the other hand, give you the data that you put into it. So the queries that you would run on a database to get data out of it, they have their own language. So it's not natural language. It's not like talking to it. You have to actually learn the query language. That query language has a strict syntax, so you have to get it right. And so there can be more of a learning curve with running queries to get data out of your database. But the data that you get out of it will be exactly what you put into it. Okay, so why did I want to try to integrate a large language model with our knowledge graph platform, excuse me. So the first reason was to try to make it easier to write queries or draft queries. So I wanted the user to be able to ask a natural language question, something like, how many people are in my database or are represented in my database, and have it automatically produce a query that would answer that question. An alternative approach that might seem more intuitive is that you could train a large language model on all the data in your database. But those models are probabilistic. So if you asked it a question that requires an accurate answer, because the output is probabilistic, it may not be an accurate answer. And often when you use a database, you want to get accurate answers. Secondly, is that because we can rely on the LLM to give us accurate answers from data in our database, we could maybe use it to produce a query that would give us those answers. So if it can write a query that would answer those questions, then we'll get answers to questions based on the contents of our database. And then finally, not only do you have to know how to write the query, and like I was saying, the syntax for the query, but you also have to know the data model. So if you are familiar with a database like a SQL database, it has tables, and those tables have columns. And you have to know what those columns are so that you can know how to write your query and what constraints to include in your query so that the data you get back will be what you need. So why knowledge graphs? So knowledge graphs provide, compared to other database, compared to other data models, a knowledge graph provides a more intuitive model for understanding what's in your database. And as it turns out, it's also more intuitive for LLMs. They expressive structure and schema. So that from the experiments that I ran and the tests that I've done, that made them made it so that an LLM could write or write a query for you that had a greater likelihood of giving you the results that you need. So some of the other database types are like relational databases, and they use the SQL language for writing queries. And so I tested using relational databases and asking the LLM to write SQL queries for me. I tested with some NoSQL databases just to compare. And then finally, I tested with some graph databases. So another reason for knowledge graphs is that they are more naturally correspond to domain ontologies, and domain ontologies are especially when they're standardized, they break down a domain of knowledge into its constituent components, and the data model of a knowledge graph just aligns with that more naturally. And as it turns out, that the more you align your data model to a standardized domain ontology, again, the greater likelihood there will be that it will produce a query for you, given a natural language question that actually answers the question. And this is another example of how a knowledge aligned to a domain ontology. Here you can see that the knowledge graph schema is sort of subordinated or is an instantiation of the data within it, is an instantiation of the entities represented in the ontology. And then also knowledge graphs can sometimes be a good first stage for onboarding new data sets. So data can come in lots of different formats. So there are lots of different kinds of formats, like hierarchical formats, tabular formats, some unstructured text. And those different formats can make it difficult to ascertain what's in the data when you look at it. So the example I'm showing here, which I know is probably hard to see on the screen, but this is a Mongo database with from a data set that we loaded into our knowledge graph. It's called the UBO data set. It contains a lot of information about companies and other entities that are related to those companies. And it's very hierarchical, and just looking at it, it's difficult to ascertain what's in there. And you also have to iterate over a lot of the data to get a comprehensive understanding of all the entities and relationships that are represented in it. So if you bring that entire thing into a knowledge graph, as you can see, it becomes clearer and more comprehensive to see what's in that data. So, and finally, as it turns out, knowledge graphs they lend themselves to simpler prompt engineering, and as I've said before, a greater likelihood of generating a correct query given a natural language question or prompt. So I wanted to compare this with something like a SQL database, because that's what I did when I set out to integrate the LLM with the property graph platform that I built. So this is a one-to-many relationship in a SQL database. In order to answer a question, you would have to, the question that I'm showing here, like how many orders were placed by John Smith, you would write a select statement that joins the order table to the customer table based on the customer ID stored in both tables. For many-to relationships, which are common in SQL databases as well, the query gets more complex. You have to do more join operations. You have to know what the identifiers are in each table. And in order for the large language model to produce the correct query, it also has to understand which one of these identifiers to use to perform this join. And in the testing that I did, I found that getting those identifiers were correct was one of the ways that it would not produce the correct query. It wouldn't understand which columns were used as identifiers. With the knowledge graph, the identifiers that are used to relate entities, that whole thing is abstracted away. So when you go to write a query for a knowledge graph, it's more expressive, and you're not dealing with those primary foreign keys or those identifiers for entities to relate them together in the query. So answering that same question with the knowledge graph, this is a graph traversal language called Gremlin that I'm showing here. It's the language that we use in the knowledge graph platform I've built. And as you can see, the query here is a bit simpler and more expressive. We have labels on the relationships between the customers and the orders and the product. And now to answer this question, I can write a query like this, which is more intuitive and expressive. So to compare and contrast those two, if the large language model had to write a query to answer the same question using the different database types that I've shown here, this is the difference between them. And so as I found in my testing and experimentation with this, the large language model produced more accurate queries when it was using a knowledge graph. So integrating large language models with knowledge graphs. And then so I'm going to go into the process, the initial process that I developed for that, the algorithm. But one consideration I wanted to touch on was whether the large language use one that's on-prem or use a SaaS. So SaaS is software as a service. That's like OpenAI. So it requires, and our knowledge graph platform gets deployed or might be deployed on networks that do not have internet connectivity. And so as a result, it needs to include the large language model capability with it. So I had consideration for actually running and hosting the large language model myself. I got as far as the GPT 3.5. I was able to run that, and there are hardware considerations with that, performance considerations. So those were some of the things I dealt with when I did this integration. And then finally not finally, and then some of the other challenges I've faced were in regards to the syntactic validity of the query that's produced and testing that maybe ahead of time. And then also the correctness of the query for answering the question. So this is something that I'm not sure we'll be able to nail down, so to speak, in that the user will have to be somewhat familiar with the query language in order to know whether or not it's correct. Or to run it and know if the data they're seeing actually answers their question, and then goes back and iterates again on developing that query. In either case, it definitely helps, as I found, to have the large language model give you a head start to develop that query. And then you can go back and refine from there. And then we're going to look at a prompt engineering example here soon, as far as one of the challenges I faced when doing this. Prompt engineering is an iterative process. It feels like an experimental process. I tried different approaches to sort of prompt the model to know about the schema, to know what all the properties were of entities so that it could generate the correct query. It also requires that you parse the output. Because the large language model is probabilistic, it's not consistent with what it produces. Almost every time it did include a query, but that query could have been surrounded by other natural language text. So I had to develop a way to extract that query out of the natural language text, out of the output, and then show that to the user and give the user the option to run the query. So here's the 3 steps generally that are performed to prompt the large language model to automatically generate queries. One is to get the schema and format the schema for the LLM specifically, and then prompt it with both the schema and the natural language question that the user entered into the system. So here's getting the schema. This is again, this is like the first iteration of this integration. So very simple function to ask the property graph for its schema. And this is a small example of the output that it produces. This is a more realistic example, just basically a blob of text. But what this is doing is it's defining the schema, it's defining all the properties and the types of those properties. And in order to prompt the LLM, I couldn't use all this, especially for smaller models. Smaller models have a smaller token length that they support. So you're going to have to, for the schema of your database, you need to remove anything that's extraneous, anything that isn't going to help the LLM know about your schema. So that's what I did. So the second step is to format this. And this is just a couple of simple functions to remove extraneous stuff that doesn't help, like defining indexes, defining partitions within your data. And so this is the function, a very rudimentary function for doing that. And then finally, prompting the LLM. In this case, I'm using OpenAI as an example. So I pass in schema that was formatted, and then I pass in the prompt from the user. And then the LLM produces an output, and then I process that output to extract the query and show that to the user. So I'm going to bring this together and show it in the platform that I developed. It's called SKG, stands for Semantic Knowledge Graph. So this is the sort of the query interface for that platform. Earlier, I showed the Mongo database that we loaded, and there was just a picture of it. So that had about 650,000 companies represented in it, along with like directors of the company and the street addresses for the company and all that. So I took that and loaded it into our knowledge graph. And the initial schema for it is basically representative of the relationships and entities in the actual raw data set itself, in the Mongo database. So I'm going to show you that schema. And so here's the resulting schema from that. Again, this is just the first stage of that loading process. From here, we would take it and refine this model, take out stuff that we don't really need, because we're not going to be asking questions about them. But as you can see, there's a company entity. It shows advisors for the company. It shows persons with significant control. These are all entities represented in the knowledge graph. So normally, and I built this platform before I integrated the large language models. So normally you would have had to write a query here. And you'd have to know the Gremlin query language. You would have to know how to write a graph traversal and what that means. And so this is a very simple query I'll run that basically says, give me back any 10 entities and traverse it to show me what's connected to them. So this is an example of a result of that query. So big blob of data here. I'm going to zoom in so we can see these entities and what they're connected to. We're currently working on the next version of this platform, so the visualization is going to get better and better. But yeah, you can see that this is a company land and site, and you can see all the entities related to it. So one of the analytic questions we had, for one of the reasons we wanted to load this data set, was because we wanted to identify companies that might have any connections to China. So I'm going to write a natural language query. So the query interface here, I wanted to show the user the schema so they could see the entities and relationships in their knowledge graph and get an idea of the kinds of questions they would be able to ask, like what's in here as they write their natural language query. Obviously, you're not going to be able to ask questions about entities that aren't in here. So, so an example query to answer that China question, something like, so we've got persons with significant control. So let's look at, oops. So which companies have persons with significant control located in China? Sorry, I used this keyboard. Yeah, well, there's a lot of ways that you can improve the performance. You can modify parameters that you pass in to the LLM, like the temperature and the seed value. And again, if there's time, I'll be talking about those. So here's the query that it generated. It looks like it's country of residence. Yes. Okay, so let's run this. I added this ability to test it, and this basically tests the syntactic validity of the query ahead of time before you run it. Later versions, as we're improving this, and we are making significant improvements, we don't think we're going to need that. So I'm just going to run this to see what happens. So it filtered on persons with significant control, country of residence is China, and these are the companies that have those connections. So it answered the query and gave us back the companies that have those connections. Anyway, you can go and explore this, traverse these entities and all that. So I wanted to go back and talk about some areas of improvement that we're working on.
Can I ask a question before you go?
No questions yet, but afterwards. Yeah, I appreciate it though, Cam. Thank you. Yeah. So one of the ways to make this better is just using consistent naming conventions for like the property names, the entity names, and the relationships. Aligning to the domain ontology that I talked about before helps with that, because that if you work to align your data model to a domain ontology, your naming conventions will follow suit naturally. And then finally, and this is one that I'm particularly here soon in the next version of our software, is associating the parameters used in prompts. So like the temperature, which the temperature setting is determining how random that output's going to be. So if it's consistently producing a good query, you could probably reduce the temperature so that it is consistent every time. But You can also modify the seed, which is if, as programmers know, the seed value is like the seed for a random number generator, pseudo random number. So you give it a seed value, it's guaranteed to produce output that looks random and behaves random, but is the same every time given the same seed. And so you can use that with a large language model. But also often the same query gets run for a given, like a knowledge graph. Often users will run the same query, just phrased differently. So maybe a cosine similarity of the natural language queries, and then associate the using user feedback. So the user gives a thumbs up on the query that was generated. You get enough of those if two natural language queries have the same cosine have a good cosine similarity, then you could just shortcut and use the one that was already generated that we know was correct. So these are some approaches we're taking to make this capability better, leveraging LLMs. So that's it. My time's up. So thanks everybody. I appreciate it.